Good.
All right. Welcome back, everyone, to the second session. So we are going from Minicrypt all the way to Obfuscation. And this will be a two-part tutorial, first by Amit and then second by Ayush. And maybe Ayush will switch over in the middle at some point towards the end of your talk.
We'll see,
We'll see.
potentially. Yeah.
Okay, and today we are going a bit longer than the rest of the days. We'll end at 5, so this will be a 2.5-hour tutorial and split into two parts. And yeah, who better than Amit to kick us off? Yeah.
All right. Thank you. Yeah. Yeah, it's really wonderful to see so many new faces. You know, the next generation is here for cryptographers. Also some old faces, of course. Yes. That's always wonderful. But it's a special treat to see a lot of new people, and hopefully I'll be able to convince all of you to work on obfuscation. So let's go ahead and get started. So I think it's always interesting to begin. Is there a weird echo? Is this okay? Yeah, okay, hold on, let me see if I can adjust this. How about now? Is that better? Can you guys still hear me? Yeah? All right, okay, very good. So I think it's always good, but when we're thinking about obfuscation, to really take a step back and think about it from a more human perspective, although kind of gruesomely human perspective, just to get a sense of how non-trivial this question is, right? So suppose for a moment that you wanted to keep a secret, right? But unfortunately for you, there's an adversary that has captured your entire brain, right? So it's taken the brain out of your head and is holding it in his hands, right? And unfortunately, this adversary not only holds your brain in his hands, but can actually read and tamper with every neuron in your brain while you are thinking about the secret that you want to keep from the adversary, right? Like, I hope this never happens to any of you. Thankfully, I haven't heard of it happening to anyone, any humans, right? But think about it. Us humans feel relatively safe. We have this nice skull protecting our brain. But poor innocent programs, this happens to all the time, right? Think about it. We actually just sell our programs to people, just giving away their brains, right? The analog of the brain is the code of the program, and we just give it away to the adversary, right? But we're asking the same question when we think about obfuscation. We're asking the question, if indeed I give you the entire brain of the computer program, I give you everything about it to the adversary, can somehow this program still keep a secret, despite the adversary seeing everything that is happening? And I want to emphasize that in this area of obfuscation, there's no trusted hardware. There's no interaction with some server that can hold some secret for you. Everything is public, right? The computer is public. Nothing about it is secret. And furthermore, the program itself can just be an ordinary program, ordinary non-encrypted inputs, non-encrypted outputs, if you would like, right? So it can be any sort of program. And that is the goal that we are trying to achieve, okay? So, and this problem has been open at least since 1976 in the classic Diffie-Hellman paper on public key cryptography. They already talked about this idea of a one-way compiler back then, some sort of compiler that can keep the secrets of the original code. But it was basically open for a very, very long time. And before we get into actually constructing it, it is actually interesting to think about what exactly do we mean. We have this intuitive idea of a one-way compiler or keeping some secret. But what does that mean? And in fact, if you think about it, a lot of programs just can't have secrets, right? Like if you have a hello world program, its only objective is to print hello world, what is there to keep secret here, right? There's nothing to do there. And sometimes you can have a program that seems to have a secret, but just is inherently bad at keeping it, right? So for example, if we have a program that has some secret S, supposedly secret S built into it as a constant, but the functionality of the program is, given the input X, it checks if X is less than S, if so outputs 1, outputs 0, right? So with such a program, there's no hope of keeping a secret because obviously any adversary, an adversary that gets any program equivalent to this program can just do binary search and obtain the secret, right? And also, by the way, I would love to have questions, so please interrupt with any questions at any moment. Hopefully this is extremely trivial and no need for any questions here. But this already gives us an idea about how we might want to formalize obfuscation. One idea would be to say that can we take a computer program and somehow transform it into a black box that is something where the only thing you can learn about it, the only way you can learn something about it is by making some number of queries, right? Just asking it some inputs, getting some outputs, and trying to obtain information that way, right? And again, hopefully you guys don't need me to say this, but in cryptography, typically, and certainly for this talk and for this tutorial, we'll be considering only computationally bounded adversaries. So when we talk about learning from queries, we mean learning from a bounded number of queries to the program. Okay. All right. So that was an idea. Can we somehow convert a program into a virtual black box? It's a very natural idea. It's a very powerful intuition, in terms of security. So back in 2001, we formalized this and then immediately ruled it out. Okay. So let me tell you exactly what we mean here, because I think it's still a very good definition to have in your mind when you're thinking about obfuscation. So I want to tell you where the bodies are buried here. So what do we mean we ruled it out? I'm not going to tell you the exact formal definition just because we're not going to be using it. So, but roughly speaking, it is somehow converting a program into a black box, right? And the way that we ruled it out was we constructed an extremely contrived program, program that at a very high level behaves something like this. It looks at the input and checks if the input somehow is actually a program equivalent to itself. Now, of course, it can't actually do things like that in general. There are lots of details hidden here, which I won't get into. But roughly speaking, it checks if the input, in fact, sequences of inputs, happens to contain a program equivalent to itself. And if the inputs happen to contain a program equivalent to itself, it just spits out the secret, just throws out the secret. And otherwise, just outputs 0. So if you think about it, given black box access to such a program, you're just always going to get 0, right? If you only have a bounded number of queries, what are the chances that you will guess a program that happens to be equivalent, in the sense of the secret? It's extremely low, right? It's negligible. And so given black box access, it just looks like a 0 function. But on the other hand, if you give any obfuscation of P, I can feed it to itself, and it will spit out the secret, right? So this idea was there. It's been improved in various ways, but all of the improvements still have some notion of contrivedness to them. And so all the negative results are only for contrived scenarios. Nevertheless, we're mathematicians, and we don't want to work with a definition for which we know we have counterexamples, right? This is not very interesting mathematically to do that. So we want to move to a better definition. And indeed, in the same paper, we considered a weaker definition called indistinguishability obfuscation, which is the focus of this talk and the focus of the tutorial and the focus of a great deal of work over the last several years. So what is I/O? I/O is a much, much weaker looking definition. Okay, so what does it say? So it's, as usual, it is a compiler, right? So you start with some program, you pass it through I/O, you get some program P tilde, and just for concreteness, let's think of the program as just being an arithmetic circuit over the field of 2 elements with n inputs, right? So just it takes an n-bit input and outputs some output, let's say single bit. Now, of course, this compiler, as always in cryptography, right, it's going to be a randomized program. That's going to be very, very important. It's also very important that these random bits are kept secret from the adversary. Only the final output is given to the adversary. And of course, it should be functionality preserving, right? So the I/O compiler shouldn't change the input-output behavior of the program, okay? And again, what that means for us in the simple case that we're looking at of just arithmetic circuits is that for all inputs in f2 to the n, P of x should equal P tilde of x, right? So it's just functionality preserving. Okay. And so far, those are just like basics. Now, what is the actual security property? The security property says that suppose I start with two different programs, P0, P1, that have the same size, so their circuit representation of the same number of gates. You can always pad it with, useless gates if you wanted to make sure that they're the same size, such that they're actually functionally equivalent. So for all inputs x, P0 of x equals P1 of x. But they're implementing the same function in different ways. And just as an example, if we just think about a simple multilinear formula, I could do it this way. I could have a plus b times c plus d and then minus ac, or I could write it in the canonical multilinear form. These are two equivalent ways of computing, a particular polynomial. And that's just one simple example to give you a sense of what I mean, that they can have different ways of implementing the same function, right? And then the guarantee says that if we pass these both through the IO compiler, and we get these two obfuscated programs, now we pick one at random, and we give it to the adversary, it should be hard for the adversary to distinguish between these two programs. Okay? And again, we mean that in the usual way. This is like how we formalize it. You guys hopefully all know how to read these kinds of definitions. Basically, to say that for all polynomial time adversaries and polynomial size P0 and P1, which are functionally equivalent and the same size, which I think I forgot to write down here. The probability of the adversary, distinguishes is bounded by an inverse polynomial for all inverse polynomials, right? Good. And so what is this definition? What does it mean? Like, what is it trying to get at? In some sense, we can think of IO as a pseudo-canonicalizer, right? Imagine we could take every program and convert it into a canonical form, right? In that way, any two programs that share the same functionality would yield the same canonical form, right? Then it would satisfy this definition, clearly, because in that case, P0 tilde would equal P1 tilde, right? Now, we don't expect canonical forms to exist for circuits. That would cause various bad things to happen complexity theoretically. Well, things that we don't expect. Actually, they would be awesome things. but we really don't expect that to be true. And that is, what IO is asking for is that it's pseudo-canonical in the sense that you just can't distinguish the two forms, right, from each other, or any form of an equivalent program. Okay. So, great. Is that clear, just the definition? Any questions about that? Yes?
Are there any other related notions of like pseudo-canonical? You got me.
Pseudo-canonical, yeah.
Are there any like in different areas, like outside crypto, like other
Good,
formalizations
yeah,
of this notion?
it's a good question. I haven't seen it. I think this is maybe the first. I haven't heard of a pseudo-canonical form before. I think it's, sorry? Well, those are actual canonical forms. I think what you're asking for is something that's not a canonical form that somehow looks like it. I think it's very interesting, and I haven't heard of it in other areas of mathematics, so that could be really fun to think about other pseudo-canonical forms, right, in different regimes. Any other questions? All right, so, okay, so why? Why should we care about IO? So the truth is, actually, when we thought of this definition, we actually weren't sure like if it was good for anything. And there were many years where we really didn't know. And then actually Shafi and Guy, right? Shafi and Guy realized that actually this definition is somehow achieving a best possible notion of obfuscation, which was, brought some excitement, although we still didn't know really what to do with it or very much about what to do with it. But then more recently, since about 2013, we've realized that we can do an incredible amount of stuff with IO. So it's been really remarkable to see all the things that have been achievable with IO. Just as one example, if you have, and for the moment, just for this slide and for the next few slides, just because it's a little complicated to talk about the actual details, just think back to the virtual black box definition, okay? Just for intuition right now. If we actually had a way of getting a virtual black box, then so many things would be so easy to achieve, right? For example, suppose you wanted to do fully homomorphic encryption, right? Well, I could just have a program that decrypts, processes the ciphertext, and then re-encrypts, right? And I just obfuscate it, and I've got myself a fully homomorphic encryption, right? So that's just one example. We can also get functional encryption, which I'll talk about later anyway, and just so many other things. And there's this really, oh, I like it, this technique called puncture programming that we developed for using I/O. I wish I had time to go into it, but I think even if I did have time, I would sap all of your remaining energy if I went into it. So I actually won't talk about how exactly we use I/O, although it's really beautiful, and I encourage you guys to learn about it. But it somehow turned out to be sort of a master tool in cryptography. If we assume that NP is not in infinitely often BPP, then I/O plus that seems to imply most of crypto. We can get lots of classical things, or let's say pre-I/O notions of cryptography fall out from it. Lots of new crypto that people hadn't thought of until I/O came along. Some of which we don't need I/O anymore for achieving them, but lots and lots of things. So rather than just reading out this list, I actually thought I would borrow this slide from Rahul. I don't think Rahul is here, right? Rahul Longo. But he kindly let me borrow his slide. So I just mentioned that I/O we came up with I/O in 2001 in this paper, but that's not the truth. So it turns out that there was a movie called The Lion King, a very excellent movie, in case you haven't seen it, in 1994, in which we have Pumbaa talking to Simba, and what most people think is that Pumbaa said, these two words will solve all your problems, Hakuna Matata. I hope, are people too young now? How many people actually have heard of this? All right, good. Okay, good. So if you haven't seen the movie, you have to see the movie. It's an excellent movie, really, really good movie. But then Rahul, he went back and he got the original script. And it turned out that what Pumbaa was saying was indistinguishability obfuscation. So it turns out that Pumbaa, in his wisdom, actually invented I/O many, many years before we did. So the reason, and it wasn't surprising to Rahul, because what he realized in some of his work is that you can use I/O even to tackle problems in differential privacy, de-randomization, logic, average case complexity, meta complexity, lots of things that seem far away from cryptography. So I/O is really a very, very powerful tool. And as a result, many different communities have taken advantage of its power. Cool. So let's do it. Let's prove that I/O exists. Let's get into the main focus of this tutorial. Well, first, let's always take a step back and recall with due humility how little we know, right? So we cryptographers, have accomplished a lot. Certainly, we can be proud of what we've done, but we also have to acknowledge we actually don't know how to prove that anything exists. Anything useful, almost anything useful. We don't know how to prove that one-way functions exist. We don't know how to prove that complex key encryption exists. And why? Because we don't even know how to prove that p is not equal to NP, right? So, sorry?
With MPC, you can prove things unconditional.
With unconditional, yes. And I'll briefly not mention that later. But yes, so, except in information theoretic contexts, which are very beautiful, obviously, but that's not the focus today. There's so much that we want to do in cryptography that we just don't know how to prove, right? And it's really sad. It's just, we have to be honest about it. Like, it's very sad, that it's 2025 and we still have really no good approaches, right? So all of you students, please prove that p is not equal to NP for me. I would really appreciate that. That would be very helpful. No, I'll mention that a little bit later. But yeah, probably not the best problem for a new PhD student to work on, but a great open problem. So, okay, so what do we do instead, right? So instead, the modus operandi in cryptography has been to use well-studied hardness conjectures instead, right? That's kind of the gold standard in our field. We want to look at hardness conjectures, especially hardness conjectures with some sort of win-win flavor, in the sense that they come from other areas of mathematics, so that if it turns out that they're not true, then that'll be really fascinating for science anyway, right? And classic ones are like factoring products of large random primes, learning with errors, discrete logarithm, LPN, a few other things I'll talk about also later on. Um, and, uh, and that's kind of what the general goal is, right? So I was encouraged by you all to recall this slide from 10 years ago. You know, we're ignoring information threaded cryptography for the moment. But in general, cryptography is all about hardness, all about the hardness present in various functions. And if you think about our field, ignoring again information threaded cryptography, it's we are like gardeners, right? So we go out and we find these little assumption seeds, these hardness seeds, and then we grow these like beautiful flowers out of them, right? So we took RSA and factoring and things like that, and we got NDDH, and we got zero knowledge and multi-party computation with a dishonest majority, public key encryption, and so many other beautiful, beautiful things, signatures and everything else, right? Out of these assumptions. And then, a few years later, we found bilinear maps and elliptic curves, and we were able to build other beautiful things out of them, like identity-based encryption, ABE, short signatures. Then even more, well, we were contemporaneously, but more recently in terms of the major effort in our field, learning with errors problem, before that Gentry's earlier lattice problem. And we got this beautiful fully morphic encryption notion out of it. And there are also these other assumptions that we've thought about over the years, like learning parity with noise, with what I call moderate error, and PRGs and NC0. We'll talk about this a little bit more later. They'll be important for us, where we can get certain efficiency, like they were kind of introduced for getting various levels of efficiency in different areas. And this has been kind of the story of cryptography, right? That we introduce these assumptions and we get some new things out of it. And I really want to make the case in a counterintuitive way, and maybe later, that we should definitely still think about all the remaining space, right? The truth is that ever since Shannon, like we've known that most functions are hard, right? Like most functions are hard to compute. And the number of sources of hardness that we know how to use in any non-trivial or interesting way in cryptography is really, really minimal, right? And especially this is true when you go outside of minicrypt. So when you're not thinking about just one-way functions and symmetric crypto, and you want to build things like public key encryption, it's, again, something we should be really just like humble about in our community, that it's 2025, right? All these years have passed since the introduction of complexity theoretic cryptography, right? Spearheaded by Shafi and Manuel and so many others, right? And yet we still know just a tiny handful of sources of hardness that we actually know how to manipulate to get advanced forms of cryptography like public key encryption. So I think this is still just a really, really important area for us to look at, and I'll talk a little more about that in a minute. So anyway, trying to scale this sort of mountain of I/O. In fact, the way that we did this historically over the last roughly decade, is through new hardness conjectures and trying to understand what's going on there. So there were these notions of multilinear maps, and there were sort of the first generation of I/O candidates based on multilinear maps, which I won't talk about. Then there was a second generation of I/O candidates based on less multilinear, but still multilinear maps. And then there was a third generation with something else, which I won't talk about at all. There are other approaches that are based on sort of variance of learning with error with various kinds of leakage, totally new hard problems like tensor products of different things and ADPs. Some of these things you'll learn about at the obfuscation workshop, by the way, so I encourage you to come to the obfuscation workshop. And a lot of work went into this, went into looking at these different kinds of assumptions and building I/O out of it, right? At the same time, it also turned out that we discovered lots and lots of attacks. So there were an incredible number of novel cryptanalysis tools that were discovered that let us attack these things. And in fact, the result that I'm going to be talking about today the intuition for that came via these attacks and these different assumptions that we explored. We really understood like where not to go, you know, what things we had to avoid based on all of this work that came in the community over the years. And I want to just make one more comment before I proceed to that. So I want to mention that, you know, when this was the state of affairs, so, you know, of course I remember it, some of the old people, you know, remember what this was like. It was bad, you know, actually. I guess I was senior enough that no one used to say it to my face, but, you know, Ayush told me that when he was giving talks about I/O that, you know, some people would go up to him and say, but I thought I/O was broken because of all these attacks, right? So there was like a lot of worry, let's say, in the community as to whether things might be broken. Yeah.
Can you comment on to what extent the attacks were on the assumptions or on the construction, and
Yeah.
was any different on the blue path or the red path in this respect?
Yeah, great question. So in fact, in the beginning with the multilinear map, candidate multilinear map constructions, they were only attacks on the assumptions. So we thought, okay, maybe it would still work out. But then actually we discovered attacks on the underlying I/O schemes themselves. These are these annihilation attacks, which I think was a novel cryptanalytic attack using annihilating polynomials that we found. There were low degree annihilating polynomials that existed in that space. And then actually so in fact, it turns out the bottom line is there were actual attacks on many schemes as well. Now, there were ways of immunizing these schemes to prevent the attacks as well, which, you know, I won't get into, but yeah.
So you're saying that these annihilating or whatever
Yeah.
attacks managed to break the assumption?
Not just the assumption, but even the construction.
No, I
No, no,
understand.
Yeah.
but if you had a
But
proof,
if they had a proof, if you had an
Yes.
equivalence proof, then you managed to attack the assumption by attacking the construction. It wasn't equivalent.
Well,
there was no proof.
It-
So there was no, that's what I'm asking.
well, no. So there were okay. There were at one stage we had proofs based on succinct assumptions over multilinear maps. Those assumptions were broken. Then we still had some constructions that were a little more heuristic, let's say, in flavor, right? And then we broke those assumptions, those constructions as
Right.
well. Then we were able to immunize them, and there are still assumptions, constructions based on multilinear maps for if we have no attacks. But, you know, it's a little tricky. Yeah. Yeah.
This entire win-win idea.
Yeah.
Goes back to Diffie-Hellman or whatever. I don't know the case where because of a type of proof
Mhm.
and an attack on the scheme, we actually broke an assumption. It would be interesting.
Right. You mean if that came first?
Yeah.
If that came historically first, that's an interesting point.
Like,
Yeah.
This actually has led us to mathematical breakthroughs to problems which are came from another domain.
Right.
Because
Right.
they made up
Yeah.
something, right?
Yeah, that's the thing. All of these assumptions were all made up and were not.
Because we wrote them directly. We didn't
Yeah.
write them.
Yeah. And
But what about the LWE side?
yeah, so these also these are much more recent, but there are attacks. So in general, with LWE flavor assumptions, there are linearization attacks. So linearization attacks are sort of the Achilles heel for most new flavors of LWE. And we're getting better as a community of discovering them, but we still
So
don't have
these
a
were
very
attacks
good
on
way.
the assumption.
These were the attacks on the assumption
Because
and
of leakage or.
because of the leakage. Yeah. Because of the leakage that was present.
It's also on the schemes, some of them, where some scheme is more complicated, some of the electoral ones.
Okay. Yeah.
I'm not sure, but
I don't know. I'm sure you're right, Sanjay. I just don't remember exactly. So I'm glad that you pointed that out. I only remember the attacks on the assumptions, but you're probably right that at least some of them were broken, even otherwise. So yeah. Anyway, so good. So at this point, actually, let me make one more point right now, actually, just because of the discussion, right? So another thing that is true, right, is that we had a way of constructing I/O based on the existence of certain mathematical objects, right? It turns out that we didn't have any good candidates for those objects, right? The candidates turned out to be broken. So that was kind of sad, right? But at least to me, if that is the case, I find it very hard to believe that the object doesn't exist. Because then you're showing that a certain mathematical structure doesn't exist. Which again, it could be true. Of course, there are certain mathematical structures that don't exist, but that would be remarkable, right? That would be another kind of remarkable win-win thing, that a certain mathematical structure can't exist. So that was always something that kept me completely optimistic that we would always succeed in building I/O. But nevertheless, it was bad. Okay, so there was a time when there was a great exodus. Lots of students, especially, were running for the exits, not wanting to work on I/O anymore, which was really sad. And I like to. The old people have always seen me say this many, many times, but lots of new people here. So there's this wonderful quote by Steven Weinberg, where he talks about, a student wanting to go into general relativity rather than elementary particle physics, because elementary particle physics looked like a mess, whereas general relativity was so beautiful, right? And Steven Weinberg said, that sounds like a great reason to do the exact opposite, to actually go for where the messes are, right? Because where the messes are is where we don't understand things, and we have like the most opportunity to actually clean some jungle, right? And actually chart a new path through something. So I would definitely always encourage all of you who are just starting out to think about it from this perspective. The areas that we understand the least are the areas that you should go into and help tame those wilderness areas. And now, I earlier jokingly suggested that you guys work on P not equal to NP. So let me be very clear about when I am joking and when I'm not, right? So I don't think you should work on P is not equal to NP unless you have a really great idea that you haven't, that we don't know.
But that's a very clean question.
It's a very clean question, right? But the problem is that when at the same time, I actually do encourage everyone to spend at least a couple of weeks in your career working on P not equal to NP, just so you can try to understand like what the difficulties are, right? And one of the fundamental difficulties, at least for me, when I tried to think about P not equal to NP, is that I have no degrees of freedom. Like, I don't know where to start. I don't know what to do. Like, I'm just stuck, right? Whereas when we were working on I/O, always we felt like there were degrees of freedom that we hadn't explored. There was never a moment where we felt like, there's nothing to do. There were always like long lists of things that we hadn't yet fully explored. So I think as long as you still have degrees of freedom that you can appreciate in the problem space, you should keep working on it. So that's why I think these two things come together. They don't work for P not equal to NP, but I think they work for other really big, juicy open problems that I think you should all try to solve. And so indeed, we did succeed in building I/O actually from well-studied hardness conjectures. We don't even need to make any new assumptions, it turns out, in this particular case, which is wonderful. So we're very happy that we were able to do this. And and I'm actually going very slowly. So actually, Ayush, I'm not sure if I'm going to have extra time for you. But so what we showed, this is with Ayush and Rachel, who unfortunately is not here, but you'll see her, I'm sure, later in the program. So I had a couple of papers, and the version that I'm presenting here, that we'll be presenting, Ayush and I, is a second version, where we show how to build I/O from 3 well-studied hardness conjectures. One is called learning parity with noise. It's sort of a problematic name, given that we're using it over a large field, but that's okay. We'll explain that one in some detail. We also assume certain kinds of local pseudorandom generators. I'll kind of explain that one a little bit. And then we also assume the decision linear assumption on symmetric bilinear maps, which is an assumption over elliptic curves. Unfortunately, I won't explain that one at all. So hopefully you can read up on it at some other point. It's a beautiful assumption, very, very helpful assumption. You can build lots of cool things with it. And one thing I want to point out is that for the settings that we use, and I'll talk more about this a little bit later, only this third assumption even implies public key encryption. So we do not know how to build public key encryption from LPN with our noise parameters. We don't know how to build public key encryption from a local PRG. We only know how to build it with from DLIN. But if we take DLIN and we also make these other assumptions, then we can actually go all the way to IO, which is also, I think, very interesting. We'll need these with a sub-exponential hardness level. I'll talk very, very briefly about where that comes in just a moment.
So,
Yeah.
so you made that remark about the public encryption because you want to say that it doesn't necessarily need public encryption, but it implies public encryption.
Good. Yeah, actually, I didn't have this in these particular slides. So very interestingly, IO doesn't actually imply hardness at all. And think about it this way. Suppose P equals NP. Then actually IO exists unconditionally, right? Why? Because then you actually have canonical forms, right? If P equals NP, then I can just find the min circuit, right? The lexigraphically first circuit that implements some function, right? So indeed, it is possible that one could build IO without making any assumptions in some weird, really bizarre way. We don't know how to do that at all. In my intuition, we would need, okay, so again, another really beautiful open problem that I would love for all of you guys to work on is to build public key encryption for one-way functions, right? Beautiful open problem. No idea how to do that. Again, I don't see any degrees of freedom. I've tried, but never even come close to building public encryption from one-way functions. Given that that is such a fundamental barrier, we expect that IO will need a public key encryption friendly assumption, right? An assumption that implies it, because otherwise it would show how to build public key encryption, from IO and one-way functions in a new way, which would be awesome, but we don't know how to do that yet, right? Great.
It's not exactly for
Yeah.
one function. Build a public key for some specific assumptions that have some specific structure. So
Right. Yeah. In fact, where did I put it? Okay, I'll talk a little bit about that in just a minute. So, okay, sorry. Let me just quickly explain what local means. So, what do we mean by a local pseudorandom generator? A local function is one where I have x, I compute f of x, and every output bit of f of x only depends on a constant number of input bits. Okay, that's what we call a local function. Goldreich proposed a way of building a local PRG back in 2000. It's an extremely well-studied, very, very beautiful area of study as well. So this is going to be important for us later as well. Okay.
You know how to build these local PRGs from others? Like what's?
Yeah, great question. So yeah, so local PRGs, as far as I know, we only know how to build them from these very new assumptions, right? These basically these average case CSP assumptions, right? So average case hardness of some kind of constraint satisfaction problem, indeed, like a constant area constraint satisfaction problem. So
That's like that's another really right to build these from some kind of classical.
yeah, that would be that would also be remarkable if we could do that. There is a connection to certain flavors of LPN, so certain Kalin flavors of LPN, but I think let's not get into that since I should probably try to finish my talk.
Wait, so local
yeah.
PRG, you're
Yeah.
saying it's well studied or not well studied? You somehow said both of these things.
Good. So so they're quite well studied by now. Yeah, so it was
And yet
proposed
we
back in
don't know how to
2000.
build it from anything except very new assumption. I just missed something.
Yeah.
Sorry.
Good. So that's okay. You know what? I'm gonna get to this in maybe next. Let me just say.
I can wait.
Okay. Sorry. Okay. Yeah. Just a second. So just hold that thought.
Yes.
Okay. Hold that thought. I want to just say. So these assumptions have lots of nice connections to classical areas of computer science, information theory, complexity theory, number theory, and algebra. But you all know that anyway. Good. So one way of thinking about the story of I/O is actually maybe a sad story, right? That we were thinking about using these new sources of hardness to build this new amazing I/O thing, right? But we actually just ended up using these, relatively classic kinds of notions of hardness, right? And the reason why I'm putting it here is because it's 2000, right? So 2000 is 25 years ago, and there have been many, many papers trying to cryptanalyze Goldratt's PRG. So it gets grandfathered in, right? It gets grandfathered in as a nice assumption, right? And indeed, that's something I want to say, that like, you know, actually, what do we mean by a good assumption? So of course, there have been many attempts to formalize this, which I didn't put them on the slide, but there have been many papers trying to understand like what makes a good assumption, right? And I would like to argue that I would like to argue for yet another perspective, okay, on this. So the argument here is that I think it's urgent, absolutely urgent, that we explore a great variety of hard assumptions, okay? And why is that? Well, why don't we do that? Well, it's because we're conservative, right? We don't want to, like if someone buys some public key encryption from us, and then it turns out that it's broken because we made a new assumption, like that would be terrible. You know, it'd be liability and all that stuff, right? But wait a second, we're theoreticians, right? We don't sell anyone anything, right? Like nothing is going to get deployed, right? Like, or at least none of the stuff that we're presenting, right? Like, you know, I mean, maybe, you know, we might start a company later or something like that, but by that time, the assumption will be well studied, right? Like when we introduce assumption, we're not going to start a company immediately, probably, right? Or I wouldn't suggest that you do so. So the point is, being conservative makes sense when deployment is imminent, but that's not us. We're theory people, right? We prove things because we love to prove things, right? We're unable to function as human beings without proving theorems. That's why we do it. Otherwise, we would do something else, right? So, you know, that's who we are. And the fact is, again, it's 2025, and we hardly understand anything about how to make hardness useful, right? We just have these tiny handful of hard assumptions that we've been able to manipulate to be able to build cryptography. So I think of it as an urgent scientific matter that, you know, our entire field, except for information theory cryptography, our entire field is about hardness, right? And yet we've only like dug a few deep holes, right? We haven't actually dug around. We haven't understood the wide field. And I think it's extremely important scientifically. And by the way, if you want to get funded, it's also good because, hey, quantum algorithms, right? So think about it this way. Think about the field of classical algorithms before we had computers, right? So maybe we had Gödel, you know, with Gödel numbers, and like very few people worked on classical algorithms before we had classical computers. Maybe soon we'll have a quantum computer. Imagine how the field of quantum algorithms will blow up after we actually have quantum computers that we can play with, right? So we don't really understand what is feasible, what is not, and especially in light of that, it is absolutely urgent that we explore this. And I think, you know, this picture applies to all scientists, you know. So as a general rule, right, you know, we're all like this, right? You know, the guy says, "Hey, where did you lose your eye?" You know, right? We're all like this, right? Like, especially as theoreticians, right? Like we're like, well, we have all these nice theorems in this area, therefore I will work in that area, right? Even if the problem is actually really far away. And I think this is really one of those areas where, you know, we need to go out into the dark and build those techniques to examine new sources of hardness, not for win-win, but for fundamentally understanding what kind of hardness is useful, why is it useful, when is it useful, when are things hard, when are things not hard, right? We have such a limited understanding of this that I think it's really urgent, especially with respect to quantum algorithms, but even with respect to classical. Okay, so that was my little spiel. Let's actually build some IO now. Okay.
I want to
Yeah.
go back to the assumptions
Yeah.
too, because I have a question about local PRGs.
Mhm.
Of course, we believe that local PRGs exist. Yeah, I don't
Right.
doubt like that's that it's a bad assumption. It's a good assumption.
Yeah.
However, like in terms of how we build, so like Goldratt and
Mhm.
PRG, again, it may very well be secure, and you're right, it's been out there for 25 years or so why not?
Yeah.
But it's you assume it's secure. It's
Yes.
different from like having, FHE based on LWE.
Well,
Like Goldach is based on Goldach.
okay, but I'll take a step back, right? I think, for example, if you look at quadratic residuosity,
Yeah.
right? How close is that from a reasonable public key encryption scheme, right? Like, it's a
That-
beautiful
that's all-
viewpoint change, but it's actually quite close to already
But
being
that's an interesting.
at least maybe I'll make the argument that I think it's there. Like, I think there too, there's a completely understand where you're coming from. Like, I understand what you're saying, which is like, in general, we don't want to just assume the scheme is secure, right? That's just
Yeah.
not a good idea, right? But that's why I think of it differently. This is just a tool, right? This is a PRG is just a tool, and we're just assuming that we have this little tool. So I would consider it a little bit more like closer to like a one-way function. Like PRG is a tool. We're not going to use it on its own. We're going to use it together with other things to build bigger things, like we're
No,
going to
of
do today.
course. No,
Yeah.
100%. I guess I'm going back to the question of,
Yeah.
can we construct these local PRGs
Mhm.
under standard assumption, under assumptions that are of independent interest, as opposed
Yeah.
to Goldach, which is
Good. Yeah, no, that's a great question. That's a great question. And I think that one way to think about it is to put on our algorithms hat, right? And say, well, do we care about KCSP? We do, right? We
course.
care about the average case hardness of KCSP. And in fact, Benny, has a very beautiful theorem that says that if there are KCSPs that are just hard to solve, right? So it's then in fact we have the pseudo-randomness of an associated local PRG.
Okay, so what you're
Right.
saying is there is actually an assumption
Yes.
that's of independent interest. That's what I
Yeah.
was asking.
Yes.
Like not just assuming that Goldach
Yeah.
PRG is secure.
Right, but I would still argue that they're still very close to each other. That's what I'm trying to make. Like a KCSP for constant K, right? Goldrake is a KCSP,
With
Right.
assumed distribution,
With
that's
with-
Goldach's distribution.
right? No, but that too. So even with Benny's result, you need to assume that KCSPs are hard
For specific.
for specific distributions, and they're like again, there are these like Levin kinds of results, right? And I love Levin, but still like Levin results, I don't know if I would count them as giving us a lot of intuition, right? But so I think we really do need to think about the average case hardness of CSPs under the uniform distribution or under other certain
Exactly.
natural distributions of CSPs.
Yeah.
Right. So I would again count that though as something of independent interest.
Yeah.
Because
Yeah.
we're also algorithms people. We're also complexity people, and we've studied KCSPs forever, right? So I think that's a beautiful question, right? PKE from KCSP, beautiful question, right? So
As a remark,
yeah.
we now have IO from sparse LPN as opposed to the sparse LPN like and bilinear map and
right, you can replace the LPN with a sparser form of.
we can replace Goldrake PR.
and the Goldrake goes away. Yeah.
Yeah, exactly.
That's what I was saying earlier. Like that's why there's a relationship between local PRGs and K-lin for constant K. Anyway, all right, let's actually build some IO now. Okay, so let's begin with a straw man. And by the way, I'm going to give you the high level picture, and then Ayush will zoom in a little bit more. Okay, so let's start with a complete straw man approach for building IO. Recall the definition of IO as a pseudo-canonicalizer, right? So hey, why don't we just start with a canonical form, right? I have a function. Let's just write out the entire truth table. If I just write out the entire truth table, that's a canonical form. Meets the definition of IO, right? Great, done, no. Of course, so why aren't we done? The only requirement that it doesn't meet is efficiency, right? It's ridiculously inefficient to write out the entire truth table, right? But this already gives us a sense of like why efficiency is going to be the key thing for us to think about. That efficiency, that's going to be the main driver of our technique that we'll talk about today. So let's actually change our perspective a little bit. Instead of thinking about IO, let's think about a special kind of leaky encryption, okay? So suppose that I had a way of encrypting our program in a weird way. Usually encryption should hide everything about a program, right? but what if we could encrypt a program in a way that there are certain functions of whatever you encrypted that you're allowed to learn, right? So encryption that is leaky on purpose, like it leaks very, very specific things and then nothing else, right? So in particular, what functions of the plain text do we care about? We care about evaluation functions, right? So think about all the f's of alpha, where f's of alpha of p is just equal to p of alpha, right? And there's 2 to the n of these, but we want all of these functions to be leaked by the encryption and nothing else, right? That's another way of talking about I/O. This is just exactly the same thing as I/O, right? You're able to learn the input-output behavior, but aside from that, everything else is kept hidden, right?
So
Okay.
it's given some secret key.
Sorry?
So this is given some secret key.
No, this is like, okay, this is where the analogy gets a little bit less complete. This is just, let's say, a public encryption function. So there's no key here. Okay, which again is weird, I agree, but it's a special encryption, okay? So in fact, though, there is a keyed version of it that is equivalent to what I'm saying called functional encryption, and Ayush will talk about that a little bit more formally. Right now, I want to keep it just high level, okay? Where what we're thinking about is encryption, excuse me, that leaks certain information, okay? All right, very good. So great, let's try to build this, right? The first thing we can do is, it turns out that there's some really beautiful works due to Abhishek and others, and Raphael also, over there. I'm just trying to think of who's here right now, which shows that actually you don't need to get all the way to efficiency right away. You can actually do it in like steps. And very roughly speaking, what that means is, instead of encrypting the program with just a polynomial size encryption, if we could somehow encrypt the program, which is in a way that's only polynomially smaller than the truth table, so 2 to the n to the 1 minus epsilon for any constant epsilon, then it turns out that you can recursively apply this and achieve I/O, what we want, okay? And this is, by the way, where the sub-exponential hardness comes in. The fact that we need to do this, actually there are an exponential number of hybrids that will show up in this recursive proof, and that's why we need our underlying assumptions to be sub-exponential. This is basically the only place where it comes up, so this is something that we'll just use as a black box, okay? So great, now our objective has become a little bit simpler. We want to encrypt this program in this leaky way with just some polynomial advantage over the truth table size, okay? There's another key problem though, which is, think about the complexity of these evaluation functions. Obviously, they're just as complicated as the original program, right? Because f alpha of p equals p of alpha means that you're running the program, right? So that's another sort of key problem that we'll have to tackle. It's an extremely complicated thing. To do that, we're going to relax our problem again, just a little bit. So let's generalize actually, instead of relax, it's actually generalization. Suppose that we don't just encrypt the program, we actually also encrypt some randomness. And now, instead of requiring that these evaluation functions just output p of alpha, we'll let them output some information from which we can reconstruct p of alpha, okay? This is still good enough, right? Because if you leak me these f alphas, I can leak the one that I want, I can combine it together and recover p of alpha, right? So this is still good enough for us to build I/O. It turns out all those things I said earlier about the recursion works here as well. And from this seemingly tiny change, we get an incredible amount of mileage. And that's because dating all the way back to Yao's beautiful work from 1986, and then combined with these local PRGs and this beautiful work of Applebaum, Sahai, and Koshulevitz, we can show how to transform any program P, any arbitrarily complicated arithmetic circuit, into a set of like F alphas where each F alpha is actually just a constant degree polynomial. The fact that it's constant degree comes from the locality of the pseudorandom generator. So this is where we're using the constant locality of the PRG in a crucial way, combining it with Goldreich. But that's already great progress, right? So just by taking these like classical, classical randomized encodings and garbled circuits, and just sticking them together with a local PRG, we've reduced the complexity of the functions we need to delete enormously, right? And so that's good, right? On the constructive side, it turns out that using elliptic curves and using this D-lin assumption that I mentioned earlier, we can actually build an encryption, a special encryption like this, that works as long as the functions are basically degree 2. Okay, so they have to be degree 2 in the following sense. They have to be degree 2 in anything that we're keeping secret, like the program, obviously, and some of the randomness. But it can be any constant degree in additional public information. And this is a really long line of work, beautiful, beautiful line of work on pairing-based cryptography, won the Gödel Prize, like lots of really, really beautiful stuff. I really encourage all of you to read about it. And this particular sequence culminated in some work, especially Wee's very nice, simple paper showed how to do this a few years ago, right? So this is good. We know how to degree 2, and we can get some constant degree. Think about it as like 16, roughly speaking. You can probably get it down to about 16 in a natural way.
So how does this
Yeah.
compare to actually I/O? Isn't this already I/O?
Good. So yeah. So the only thing, right? We seem like we're almost there. The only piece that it remains is that this constant degree is like 16, whereas we only know how to do degree 2. Okay. So that's it. That's all we need to do. We just need to reconcile the gap between degree 2 that we can use bilinear maps for, and let's say degree 16, okay, that we get from Yao and local PRGs, okay? And yeah, this is just very high level. I'm not giving the details of this because it would just take too long. But reconciling this gap was what the focus of the remainder of this talk and also the next talk will be, okay? All right. So let me first just rename things to make things a little bit easier to talk about, right? So recall again, we want to have this encryption of P comma R, learn these F alphas. So, and we want the size of the encryption to be the size of the output of these F alpha, or like the number of these F alphas to the 1 minus epsilon, right? Think about it as the size of the output, right? Like the size of the truth table, right? We're just going to restate it. So instead of P comma R, I'm just going to call that X. So we're going to encrypt some X. There is going to be this function. These functions are local. That's also something that is true. When you use the local PRG with garbled circuits, you get local functions out. The output is Y, which is the truth table, roughly speaking, or like all the different parts of the truth table. And we just want that the size of the encryption is the size of Y to the 1 minus epsilon, okay? So this is our goal. And I hope I have roughly convinced you that if we can do this, then we're done. That makes sense? Any questions about this? Yes?
I'm not sure I understand what the R is doing there. Like, why did we do that?
Why do we do it? Yeah. So why do we do it? It's because, let me go right here, right? So think about Yao's garbled circuits. Do you know Yao's garbled circuits? No. Okay, sorry. Well, there's this beautiful, very powerful technique called Yao's garbled circuits. And it's generalized to a technique called randomizing polynomials or randomizing encodings. And as the name suggests, they're inherently randomized. So roughly speaking, the need for the R is to allow us to randomize this construction that gives rise to these F alphas that allow you to recover the output while hiding everything else, but don't just give you the output. So yeah, I'm not sure how much more I can explain that without teaching Yao's garbled circuits, which I don't
Okay,
have
can I
time
just
to
ask
do.
one more question?
Yeah.
Okay, so definitely the art isn't just important in like the end. Okay, like actually I think I understand. Okay, cool. That makes sense.
Okay, very good. Any other questions about that? Just about the goal and that this is sufficient if we can do it. You know, taking on faith the things that I have mentioned follow from previous work. Question? Yeah.
Do we need R to reconstruct the alpha? I think
We do, yeah. So the construction of these garbled circuits is inherently randomized. So you learn these randomized outputs. It's kind of like secret sharing, you know. You kind of learn secret shares of the output that you then combine to get the actual output. Okay. Good. Okay. So let's see how we can do this. Very good. So I want to just point out immediately that, you know, this function, even though it's just a constant degree polynomial, it's still doing lots of interesting things along the way, right? Like the intermediate values of this computation are going to be potentially very revealing, and we can't reveal them, right? So we absolutely need to hide every intermediate computation value. And that's something to keep in mind, just like why this is not easy, okay? This is going to be difficult because of the fact that we need to actually hide the intermediate computation values. And what are we going to try to do? We're going to instead build a system where we'll have some degree 2 computation, because remember, with bilinear maps, we are able to compute degree 2 functions in secrets, okay? And separate from that, we'll have another computation that's done in the open, so done in the clear. Think about like FHE style things, right? So like, you know, you can do FHE computations on ciphertext in the clear, right? You don't need to hide them because they're still encrypted, right? So we want to somehow transform this F into a part that is public, that gets computed on publicly, this public part Q, and some encrypted secret S, okay? And we should be able to obtain Y through some public computation on Q, together with the degree 2 computation on both the output of the public computation and the S, okay? And just to think about that formally, right, what we're saying is that the final output is degree 2 in the S's, but the coefficients of this degree 2 polynomial can be a constant degree function of the public parts Q, okay? So this is what we know how to do. So again, using bilinear maps, we know how to compute things that are of this form. The question is, how can we massage a constant degree function, local function F, into this format? Can we somehow compute F in this weird way, despite the fact that the final computation is only degree 2, whereas this is degree, let's say, 16? Okay?
The only reason you need that the public thing is constant is just for efficiency. If you can compute the CIJFQ efficiently, then that's all you care about, right?
Okay.
Is there another reason why you need them to be constant degree?
Yeah, so we can do that. Okay, so so I'm going to now say things that maybe not everyone will understand, but you know how like in ABE, right? AB does some sort of enforcement of the correct computation, right? Similarly, this bilinear map stuff here will enforce that you're doing the correct constant degree computation. And that's why it has to be limited in some way. Now, constant degree is sufficient. In fact, we also know how to do things like NC1, like we can go a little bit further.
Yeah, got it.
But it has to be limited because of the fact that we're enforcing correctness.
Got it.
Okay. Yeah. Very good. Okay. Okay. So and then what's the efficiency goal? The efficiency goal is that the size of both this public input and the secret input should be polynomially smaller than the output, right? That's the objective. If we can do that, then by what I've said already, we're golden, right? Okay, this is restating the problem. Now comes are the use of this assumption, this LPN assumption over large fields. So let me just remind you what the LPN assumption is. In the LPN assumption, we just take a completely random matrix A, okay? And we have this kind of ciphertext, okay? Which we think of as being A times a secret vector S, and the secret vector is much smaller, so this A matrix is, very, very tall and not very kind of skinny and tall, right? And now, of course, if I gave you AS, of course, you can just use Gaussian elimination, recover S. So there's nothing hard about this so far. And the beautiful thing that's been studied for decades and decades and decades in information theory is that if you just add a sparse error to this, then we have no idea how to solve this. In our setting, this error will be sparse in the following sense. Almost everywhere it's 0, but wherever it's not 0, it's sparse and large. So it's actually a random field element from FP. And think of P as being a very large prime, okay? So there's a tremendous amount of error. It's very different from LWE that way, right? So for those of you who know about LWE, the errors are always small, but they're everywhere. In this case, this is very sparse, but where the errors are there, they destroy all information, right? And the error rate that we will care about is going to be inverse polynomial, but for any inverse polynomial. And just very briefly, this is my own, And then, of course, what we're assuming is this is hard to distinguish. You can't distinguish between this and just random, okay? And this is a long history of study encoding theory. The best known attacks are sub-exponential, so we have a fair amount of confidence in this assumption. It's been studied for many, many decades. So I want to briefly mention a little bit about this error regime, okay? So these are my own names, but roughly speaking, you can think about several different error regimes for LPN. What I would call the very low regime would be where the probability of an error is only polylogarithmic over k, okay? Which means that there's still enough error that we can't just find places without error and just solve via Gaussian elimination, but just barely. And it turns out even here, we don't know anything better than a quasi-poly attack. So even for this extremely low regime, as far as we know, this is secure. And then the low regime is inverse polynomial, but where delta is at least 1/2. So it's like 1 over square root of k and lower, sorry, and lower, right? The bigger delta is the lower the error. And this is what's called the Aleknevich barrier. So back in 2004, Aleknevich showed, 3 or 4, I forgot, anyway. Back in 2003 or 4, Aleknevich showed that these regimes are sufficient to build public key encryption with LPN. But all of this is open, so we don't know how to build public encryption with any of these other error regimes. The regime that we'll be looking at is what we call the moderate regime, which is 1 over k to the delta for any delta greater than 0. Maybe high error would be like 1 over polylog error. That's enormous amount of error from the point of view of algorithms. Let's say very high would be a constant fraction, like a constant fraction of the information is just destroyed. And then ridiculously high is like 1 minus the low of 1, like that, in which you actually destroy almost everything, almost all of the output. All of these things we don't know how to build public encryption from. So we're in this moderate regime. Okay, very good. Is there any question about that? Sorry, any question about just what LPN is? Okay, very good. So now that we have LPN, observe that we can use it directly to symmetric key encrypt the input, right? So I can just take my AS plus E and just add X to it, the input, right? This is symmetric key encryption, not a public key encryption. But this is really nice. Actually, really, really nice as an encryption. Let me tell you why. And sorry, the secret key here is going to be this S prime. And just to be clear, the reason why we're calling it S prime is just to make the point that if we set up our encryption scheme this way, observe that decryption is just an approximate linear operation, right? All I do is I take, AI comma CI, inner producted with like minus S prime comma 1, and I actually just recover XI plus this very, very, very sparse error. So most of the time, I'm actually just getting XI, right? which is really nice. It's really, really beautiful that it has this property. And I'm just going to call our actual secret S to be this minus S prime comma 1. Okay. Now, why is this so nice? What this means is that actually I can do any constant degree polynomial evaluation also in a similarly nice way. So why is that? Think about it this way. What I'll do is I'll think of my secret key now and just tensor it with itself d times. Think about what that means. That just means we're getting all degree d and smaller monomials in S, right? So I'm actually just getting all of the monomials now in terms of our new secret key. And as a result, what I can do is I can just take the ciphertext, these CTIs, and just operate on them directly to pick up the monomials that I want, right? I can pick up the monomials that I want, and in this way obtain any monomial in the X, any constant degree monomial in the X. Does that make sense, right? And observe that the error will also propagate. So this will be, this will end up being like f of x plus e, which we can think of as being f of x plus some sparse error, right? And again, here we're using locality again, right? Because, you know, if f of x is local, that means every output bit only depends on a constant number of input bits, which means there's only going to be error here if one of these had error. But each one only has error with probability 1 over k to the 0.2, right? So very, very unlikely. Okay, so again, if we have sparse input error, if we have sparse input error, we have sparse output error, which is again just like O of 1 over k to the 0.2, right? So this is really nice, right? We can now have a, remember S was really small, so even S tensored with itself d times will be small. We'll just pick it in such a way that that's still small. And and in this way, we're obtaining f of x plus some error as an output. And I'm now going to try to like put this together just so you can see how it fits into our picture, right? Think of the public part as just being this encryption, AS plus E plus X, right? This constant degree part is just like building that combination of ciphertexts, right? Just the ones that's picking up the right monomials for evaluating F, okay? And think about this S as just being our secret key. You know, I can decrypt not just in degree 2, I can decrypt linearly. I have a linear decryption now. This S is like S to the D. I don't know if I wrote that here. Yeah, here it is. Okay, sorry. Stopped working. Sorry. Okay, I don't know what's going on. That's all right. Okay. I seem to only be able to go forward, which is fine. So, right, we already have this just approximate linear decryption, right? And if we just did it straightforwardly, let me just pretend this is not here right now, okay? If we just did it straightforwardly, then we would get y plus this sparse error, right? So we're like almost there. We've almost got y, just annoyingly is slightly corrupted in terms of error, right? So really the only thing we need to do is get rid of that error. So one naive thing is we could just like add the error vector to the secret part and just subtract it. But that doesn't make sense because the error vector is the same size as y, so that will get us no compression whatsoever. So we can't afford to do that. Can I go forward? Okay. So what we need to do is find a way of compressing the error vector. Okay? And this is actually where we're going to use a degree 2 fact. So we don't even need degree 2 so far, right? We're going to use the fact that we have degree 2 computations to non-trivially compress this error. Does this make sense? I'm sorry, I wanted to actually go back, but please do ask questions if you have a question about it.
Yeah, I have a question. So
Yes.
You start, there's the initial error, and then there's error that you get from the computation.
Yes. Which is still sparse.
Which is still sparse.
Yeah.
But the error, you're saying I'm going to encrypt the error. The
No,
error
no,
is,
we can't do that. This
No,
is
I
a straw
know, I
man. Straw
but
man.
I
Yeah.
know, but
Yeah.
suppose it was, because you're saying I need to shrink it.
Yes.
Suppose it was shrunk
Short
already.
somehow. Yeah.
Suppose it was short. But I'm still confused because it seems to me like at the error that you want to encrypt,
Mhm.
it's the error that you get after you do the computation.
Yes.
But that depends on the computation.
Yeah. Good. 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 But remember that F is public, right? Like everyone knows F is just computing.
It's a fixed thing, so
F is a fixed thing. Like we're just computing the truth table, right? So
okay.
we already know
Got
what
it,
the
got
error is going to
Okay,
be.
okay, so
right?
basically you compute the error before
Yes.
you win, then you're gonna.
We
not-
already know where the error is because we know what the actual truth table is. We know what we got here. We can just subtract, see what the error is. And all we need to do is compress it. So now the only remaining thing we need to do to build IO is figure out a way to compress the sparse error with degree 2 computations. Okay, that's it. That's all we have remaining. Okay, and so let's take a look at this compression task. Right, we have this error. It has a fair number of spread out errors throughout it, something like O of 1 over k to the point 2 fraction of errors. Right. And we want to somehow compress it using a degree 2 operation. So let's start with a very simple case. Suppose, in fact, the error only had one place where there was an error. Okay? Suppose we just had one location, right? If it just had one location, then this is really easy to do in degree 2. How? I can just take my error, rearrange it as a square matrix, right? Just like, wrap it up in as a nice matrix, right? It's only going to have one non-zero point. It's the rank 1 matrix. Since it's a rank 1 matrix, I can just decompose it into u dot v, right? And the dimension of u is square root of the matrix, and the dimension of v is square root of the matrix, right? So I get very non-trivial compression if I only had one error. Does that make sense? It's a very simple, very cute trick, right? Okay, now of course we don't only have one error. We actually will have a lot more errors, right? So what do we do in that case, right? When we have a lot more errors? Well, the thing that's going to help us is that we don't have to worry about worst case. These are random errors, right? In fact, we randomly put them in. Like, when we obfuscated the program, we randomly chose the errors, right? So it's going to the error, because it's average case, it's going to behave in very nice typical ways, right? And in particular, what that means is that I can just arrange my error thing again into a nice square, but then just subdivide it into lots of little squares, right? And by typicality, I can argue that each individual square will have at most, let's say, log n positions that are non-zero. And then I can just apply the same trick to each one. And it turns out that if the error was like 1 over k to the point 2, then the little guys would be like k to the point 1 by k to the point 1. Okay? And again, if you just do like a simple turn-off bound, you'll see that with very, with high enough probability, there are only going to be like logarithmically many errors here, right? And that means we can just, take our just make our u and v a little bit wider, make them like log by t to the point 1, and then I'll be able to recover these portions. Question?
Yes, because the error depends on the computation, do you need to randomize the computation, like randomize the coding style, in order to make sure you have like this average case distribution?
Good. So actually, that's not needed for a very simple reason. That, remember, we are the obfuscator right now, right? I myself am choosing the E for the LPN assumption, right? So I'm going to choose it to be typically random, right? The only thing that I skipped over a little bit here is that the F itself, in fact, it turns out, I think now I understand your question. So it turns out that we don't need that part of the F. Like, in fact, even if F is worst case, just the fact that it's local is enough.
Okay.
Like, basically, the new error ERR vector is still really, really close to being just random, or close enough,
Okay,
That-
we
that-
credit the original randomness even through a worst case function.
Yes,
Okay.
yes. As long as it's local. That's all we're actually using. Great question, though. Very good. So if we just do this for each one, we stick them all together, and note that that means we're still going to save a k to the 0.1 overall, right? This whole thing together is the size of y, right? And we're going to get the size of all these u's and v's is going to be like the size of y divided by k to the 0.1, right? So we still end up getting an advantage, and that yields the result that we wanted. And in the end, we are able to build IO that way. Does that make sense? Any other questions about this? And again, Ayush will go into this a little bit more detail, right? Yeah. So you'll hear it again in some sense, but still, this is a good chance to ask
Can you
questions.
say a bit
Yeah.
more about, I think that's a constant degree part, but like the fact that the evaluator can obviously, choose its own computation or, deviate from the AB style property that you were referring to Yael, right? That you want to enforce some AB style property, correctness of computation, right?
Yeah, good. So the thing that I skipped, that I didn't go into detail on, is that we can't just use a degree 2 bilinear, functional encryption scheme. We need the underlying special encryption scheme that uses the bilinear map, not only to do this degree 2 part, but also to guarantee that you actually did the correct public computation, right? Because we need the person who is going to use this obfuscated program to do the right thing here, right? If he does some other computation, then all bets are off. Like, we just don't know what to do in that situation, right? So in fact, using bilinear maps, not only can we handle degree 2 functions here, but we can also enforce the correct public evaluation.
You didn't go into that part in this talk.
No, no, just
No,
There's-
just to say that there's a black hole here.
yeah, this is it's really beautiful, and it's, again, it's many years of effort of us figuring out how to do that. It's just, it would take its own tutorial. Yeah, it would be its own tutorial to go over, at least an hour, just to describe how to do that.
And maybe
Yeah.
one small point, maybe you can also say like why LWE doesn't quite work here. I mean, the linear decryption property is there, but yeah, why doesn't fit well?
Yeah, no. In fact, right, the reason why it doesn't work is that this property is simply not true, right? If you try to do this with LWE, the error vector would be completely dense, right? There would be no missing parts, right?
You're talking about why can you do LW instead of LPN?
Yeah.
Or why can't we use LWE instead of LPN,
LPN.
right? And it's because, yeah, we wouldn't have the sparsity. This trick only works with sparsity, right? And it's actually very interesting. Like, with LWE, in some sense, what we're using here is that sparsity is degree 2 friendly, whereas smallness is not degree 2 friendly.
Yeah, but
Right?
relatedly.
Yeah.
And I'm more interested in, do you think there's any hope to actually get rid of the bilinear maps and instead use LPN and LWE for that part? Because what are you using there? You're using degree 2.
Absolutely.
we don't-
Yeah.
we didn't-
No, so good. In terms of, maybe I'll just skip ahead to the open questions at this point. So, there's still so much we don't understand. Like, we just finally got the first provable scheme under assumptions that we believe that we don't think are going to get attacked, hopefully, soon. Although one of them is already quantum broken, right? Like, bilinear maps are elliptic curve based, so it's quantum broken. So we definitely want to get, simpler schemes, other things, and definitely post-quantum security. And the most natural thing to do is to try to look at where we were using bilinear maps, which is to get this degree 2 computation, and get it with LWE instead.
Or
right?
LPN.
Or
Because
LPN,
L-
yeah.
The LWE, there's always the noise and how you get rid of it. But
Yeah.
LPN, it's like, there's some good
Yeah.
probability you don't have any noise.
Yeah.
you
Yeah.
know?
No, it's a great question, right? And we're still just kind of stuck on doing that as a community. We've tried a lot, obviously, as you can imagine. We're still stuck, but That's why all these people are here, right? All these young people will solve our problems for us. You know, academia is one giant, you know, pyramid scheme, right? So you guys are buying in at the next level. Yeah, lots of great questions here. With that, I'll finish. Questions? Okay.
And then we have a break.
So the quadratic forms, the elliptic, we use for varying